Welcome back, everybody. This video we're going to take a look at heat curves. Specifically what that means is, if we're talking about a curve, we're going to obviously be looking at a graph. And so what that's going to mean is we're going to have some data. We're going to have some points that are going to be along a graph. And when we're talking about heat, in relationship to matter, we're actually looking at states of matter or phases of matter. And we know that matter goes through multiple phases, and that usually depends on the amount of heat that has been, for lack of better words right now, absorbed by the matter, which, and depending on the amount of heat, can affect, the way things expand or contract, right? So a heat curve is a way of putting all that into perspective in how matter changes form, its phase, depending on the amount of heat that is present, that can be measured, that is being absorbed, that's being released in the matter. So let's just go ahead and take a look at the video. Heat curves. You'll notice from this graph that there are a couple of points here that you need to first look at, as you will with any graph. Understand your x and y, and so we can see here y is a change in temperature, so that obviously relates to the concept of heat. Then we also have this x-axis that is unlabeled, and if we were to just stop and think about this for a moment, we realize it's pretty easy to figure out that time is probably a good x-axis, a good independent variable to have right here, right? Because if we change time, let's go with minutes as a unit. Over time, if the temperature is increasing, you would see something go from a solid to a liquid and then eventually to a gas if you had the temperature increased high enough. So this is something we're familiar with. There's a couple things we need to look at here. Second part is, we call this thing a heat curve, right? And so a heat curve has everything to do with the fact that our curve has everything to do with the fact that when we're looking at graphical data and we see a line in some way, doesn't matter if that line is showing positive, negative correlation, if it's doing a lot of bending, if it's straight, they're all called curves. And so this line here implies that there's a curve, there's a change that is occurring at various points. As time is increasing, then as temperature increasing, we're seeing a correlation, and we see a positive correlation, obviously, because we see a slope, an upward slope, where there is a slope, where there is a change. So now that brings us to this next part here. Is we notice that there's two points on this graph, here and here, where there seems to be little to no change. And this graph is drawn very cleanly. These lines are perfectly straight, connected this way. They're perfectly flat this way, perfectly flat here. And in real life, as you've learned from math class or other science classes, it's very difficult and it's very uncommon for you to get exactly perfect points that are exactly 100% linear and don't sort of go back and forth a little bit. Like, for instance, if you were to draw a graph in math class, and you had a line like this, a slope. Well, more than likely, what happened was there were a variety of points along the graph, and then what you did was draw a line that best fit the points that were there, but it didn't intersect all of the dots, all the points on the graph, right? All right, so just keep that in mind, that is, what your math teachers have taught you. That is, it's very much true here still as well. Okay, so, but the concept is here it is constant. So when we're at a constant temperature, that is whatever that temperature is there. We don't know what it is. We don't know what substance this is. This is just a general substance. So I'm going to put right here some substance. We don't know what it is. It's just some substance, whatever it could be. So whatever that substance is, so long as it's at this temperature or below, it will be in solid form. However, if we have that liquid that same substance is in liquid form, when it gets to that exact same temperature, it will also begin to freeze. It doesn't immediately freeze all of it. However, it does begin to, the particles do begin to come together once it gets to that point. And you know the definition of the whole kinetic theory of matter thing, that if you have liquids and you decrease the temperature, you decrease how fast the particles move. Decrease how fast particles move, they come closer together. They're still moving because there's kinetic energy in the structure of all the atoms that are making them up. So, but eventually they get to this point, and they're so close together that they cannot flow around each other anymore, which now it gives you the definition of a solid. So there comes a point when your liquid and your solid are both at the same temperature. So we call this both the freezing melting point. Okay, this is called both the freezing and melting point. Okay, so we would say that this range right here is both the freezing and melting point. Pretty easy concept. Now what we do need to see is that from this range of time to this range of time, we know that there is a change of time here. That's just delta. Delta means change. Lowercase t is time. Capital T is temperature. Now if we write that out. So right here, there is this change. There is, in this change of time, things are staying constant. And we call this the latent heat of fusion. So let's just break this down for a second. We know fusion means things are kind of close together, right? So if you've got a solid, particles are close together, they're sort of fused together, right? Heat, when we're talking about temperature, we just got to understand what latent means. So latent, it means hidden. Latent sort of means hidden. So hidden heat, what we mean by that is this, is that at this point here, your temperature probe, if you're at this point or below, the temperature probe will be able to measure this. But right here, think of water. When water is frozen and it's ice, it's in solid ice form. When it reaches this point here, it is still at its freezing point. However, you do begin to see it melt. And as it's melting, both the ice and the water are at the same temperature. But there's enough heat that's being absorbed to break the bonds that are keeping these particles close together. And we call that a hidden heat, a latent heat. And the thermometer is not going to pick that up, at least not the ones that we're using. So you would need much more sensitive equipment that could measure this right here. There's also mathematical calculations, if we knew some more chemistry, that we could also do. But once you get to this change in time, this point in time right here, however long that is, it depends on the circumstance. There's a lot of circumstances. But generally speaking, it's going to take some time. Then all of a sudden you would begin to see the temperature increase. And that increase in temperature, right there, the temperature probe or your thermometer, it will pick that up and you will begin to see the temperature increase. It's because all of the substance is now in the liquid phase, no longer in the solid phase. And you would see that temperature rise fairly rapidly. You know, we could, if you measure this period of time here and measure over the same period of time, you could see that that's a pretty rapid increase. It's going to change very, very quickly. And just think about whatever you notice this at home. If you have something cold sitting on the countertop, on a tabletop for a period of time, it doesn't take too long for something cold to suddenly become more like its room temperature. That it's going to lose its temperature. It's going to increase in temperature fairly quickly. It's going to absorb all of that heat that's around it. Okay. So I want to look at this section here real quick before I then talk about these sections here a little bit more. Up here, So we know that from here, and I'm just kind of measuring down. This range of time, notice the same thing is happening. The liquid, when it gets to this temperature, whatever it is staying at that temperature as the particles are vaporizing, as they are moving towards becoming gas. As those particles are moving towards becoming gas, the temperature stays the same. And once the particles that do go into the gas phase, they have finally risen past that temperature point. And if you were to measure, if we were like talking about water, we were measuring the steam, it would be gas, it'd be water vapor at that point. Heated water vapor, it would show an increase in temperature above this point right here. So we know that if it doesn't matter what we're talking about, but when we reach this point where a liquid turns to a gas, we know that this is called the boiling point. That period of time where the temperature stays constant as a liquid changes phase to a gas, we call this latent heat of vaporization. And that's sort of easy to remember because there's the word vapor right there, and you already know this without being in chemistry class, that a liquid goes to a gas, and you've heard gases called vapor. So think of water vapor. And that's kind of an easy way to remember that, something you're familiar with, so it's not completely new. Shouldn't be too difficult. But also now let's go back in reverse. If you have a gas, and you're up here above that temperature, right? Here's a temperature where it's all the same, but if you're above that, you've got a bunch of gas. If this gas begins to decrease in temperature, it will condense. Particles will come closer together, and they reach this point here. And as they get to that point, once they condense enough and get to that point, you will see the liquid. You will see them condense, and you will see the liquid at that point. And then eventually it all does, and you can see the temperature drop. So this curve can be measured in two different directions. So if we were to actually, so for instance, sometimes, like let's put this in reverse. So I'm going to take this right here. I'm going to start here and just trace down this way, but over here. So this decreases, it stays the same, and then it decreases again, stays the same, and decreases again. So if you notice, all I did was take this line and flip it 180 degrees. When you see it this way, we refer to it as a cooling curve, because we have a change in temperature. Here's a change in time, lowercase t. So obviously if the temperature were to decrease over time, the substance would be cooling off. All right. And one last thing. So the section, the section right here, and let's say the section right here. Okay. When we're talking about these parts right here, where we said the thermometer could actually read, give you a specific reading, we actually call this specific heat of a substance. You can specifically measure, using the scale of your thermometer or your temperature probe, a change in temperature as the particle is absorbing the heat that's around it, whether or not that's the heat from the air, if it's on a stove or a hot plate, a burner of some type. You can specifically measure that change in temperature. All right, and specific heat is basically the amount of heat to increase 1 degree Celsius of mass. Specifically, a kilogram of mass. So if we had, what this means is 1 kilogram of water to go from, let's just say we're right here at 20 degrees Celsius. To go from 20 to 21 degrees Celsius, specific heat would measure the amount of energy to change 1 kilogram of water from 20 to 21. Okay, and pick any number. I just happen to pick 20. Okay, so this is the basics behind a heat curve, specific latent heat. We will need to know this. You're working on some stuff as well. More than likely you have been or will be assigned, so you can use this to help you out. If you have any questions, be sure to bring them to class or email me. I'll be happy to answer. Take care. So as you can see, for the heat curve, everything we're looking at basically the concept of, is this matter in a solid, a liquid, or a gaseous vapor like phase. We typically leave plasma off of that because we're talking about things as hot as like the sun or lightning, and so that's not that would be something completely different and graphical, because the temperatures for those would be way higher than what you have down here for like the temperature you would have for like ice or liquid water or water vapor. So the temperatures tend to be very drastic. So you tend to see plasma graphed differently. But that generalized heat curve on there, the lines were nice and sharp. But that generalized heat curve means that you can expect to see a basic shape like that with very good measurements, very good readings. So I hope you enjoyed this video. Look at it as much as you need to. We'll be taking data in class and taking a look at that, plus stuff that I'll be uploading for you online. As always, do your practice problems. Stay curious. It's good talking with you again as always. Bye.